This is Timothy Wood with the Citadel Civil Engineering. This is CIVL202 statics. And in this lecture, we're going to be talking about what happens in non-concurrent force systems, expanding upon our vector representation of forces, and talking about what will happen in these non-concurrent force systems, particularly where we will generate moment. So let's jump right into it. So the first thing we want to talk about is our non-concurrent force systems, which are going to end up having forces. Now, we got to remember our definitions. A concurrent force system had all of the forces passing through a single point, but as we can see in this case, if we extend their lines of action, the forces don't have single intercept points. Rather, we have multiple intercept points, which means that our forces are now going to be separated by a distance. Forces separated by distance. And this distance means that we can now start talking about rigid bodies, because rigid bodies have length, and if we can separate the forces, putting them in different places, we can have rigid bodies, which we will recall. With rigid bodies, we're going to model both mass and length, hence that distance piece tying in to the length there. And what this gives us is a potential for rotation. So when we have a non-concurrent force system, our forces no longer intercept at all the common points. They're going to be separated by distances, which means that we can model bodies that have length, and we're going to tend to get rotation. Now, when we have these forces acting at a particular length, what we're going to end up calling them, they're still going to have forces, push or pull, but that tendency to generate rotation, we're going to call a moment. You might know it as torque, especially my mechanical engineers. Typically, we think of moment as causing something to bend or to flex, whereas torque, we're looking at a twist along the axis, but it's functionally the same process. But we're talking about a moment, and so this is going to be the tendency to cause rotation. So moments tend to cause rotation. It's important to remember that we're talking about statics, and so nothing's going to move, but these moments are going to try to cause things to move in this case. Now, this is a vector quantity. We're going to use an uppercase M with a hat to indicate our moment, and the way that we solve for this, or that we calculate this from a particular force, is by using a mathematical cross product. We'll talk about that more when we look at 3D moments, but for the moment, it's, no pun intended, it's worth noting that we're going to have a moment where R, hopefully remember R is our position vector. Remember, we're not putting anything down. So our position vector cross F. So we're going to do a cross product. This would require us to know something about vector mathematics. If you've seen this in Cal 3, you're ahead of the game. If not, we're going to talk about it all in this class. It's going to be okay. The order matters here. We want to do our position vector first and our force there. So this force, this is going to be just some force. R, this is the position. So this is the position, or we might even call this the lever arm. Maybe that's a concept you're familiar with. Lever arm from some distance or from some point from the axis of rotation. Oh, kind of ran out of board there. Axis of rotation. And then this M is going to be our resulting moment. So that force is still causing a push or pull, and this M is going to be our moment, that tendency to cause rotation. Our moments are going to have a magnitude. So we're going to ask ourselves, how big are they? The magnitude. And if you'll recall, our magnitude from a cross product is going to be this quantity. So our magnitude is going to be equal to the magnitude of the two vectors, r and f, times the sine of the angle between the two. Okay, so that's exciting. We can work with that. It's great. No problem with that. Now, what the sine does is it actually helps us identify either the perpendicular distance or the perpendicular component of the force. So this feels kind of mathy. Mental model might not be super strong. So another way we might express this, and the way that I find most helpful, is we can think of this as the perpendicular distance. So I've done a little subscript inverted T, that's a perpendicular. So our perpendicular distance times the whole force. So we're looking at the perpendicular distance from our axis of rotation to the line of action for the force. And I'll show us a picture of what that looks like here in just a second. Alternatively, we'll get exactly the same answer if we think of taking the whole distance and multiplying it by the perpendicular component of the force. And it turns out if we want the perpendicular distance, that's going to be r sine theta. And if we want the perpendicular component of the force, that'd be f sine theta. So it's just two different ways of doing the mental model. Sometimes this really helps us out along the way. So this is our perpendicular component of the distance or the perpendicular component of the force. We also have to ask ourselves about the direction of our moment. So our moment is going to have a particular direction. And in this case, that direction is thought of as being around a particular axis. So in 2D, it's always going to be around the z-axis or in the k unit vector direction. And what we'll use is this cross product actually gives it to us. If we remember our definition of a cross product tells us gives us a vector that is perpendicular to the plane defined by the other two vectors. So if we have two vectors like so, we're going to use our right-hand rule. So I have one vector and then my second vector there. So I have those two at 90 degrees or whatever angle they're at. And then my thumb, right-hand rule, tells me that perpendicular force. So that's what the cross product is doing there to the RF plane. And we'll use our right-hand rule, RHR, right-hand rule, to define this. And so if I think about a cross product, I would draw R in the positive R direction, F in the positive F direction, and then my thumb comes out of the board. Okay, so maybe that's not helpful to us because we're thinking about rotation. So let's come up here and take a look at this force A and think about it. First, I need to identify some point that I'm going to model the rotation about. So there's my point O. And I need to find let's think about it in terms of our perpendicular distance to the line of action. So there's my R times A. So one way that I can do this is I can do R cross F. So you can see where my middle finger is now pointing in the same direction as the force. And then my thumb tells me that it's a positive moment that force A is going to generate. Now, there's another way that we can do this if you don't want to, risk flipping anybody off. If we start at O, we can take our whole hand and point it start at the axis, point in the R direction. And then I curl my fingers in the direction of the force, and then my thumb tells me that that's in the positive direction as well. The net result of this is if we think about this force, one other way we might do our mental model is we might think of that force, it's pushing, right? So maybe it's like a rocket on a string, not an idea that I suggest you do, but if we put a rocket on a string, it's going to spin, right? And so if we look at it in this case, here's our point, here's us standing here holding one end of the string, there's our position vector, that's the string, and then that rocket is causing a counterclockwise spin. So our right-hand rule tells us that our counterclockwise rotation will be positive, or if it's going in the right-hand rule, positive z direction out of the board. So that's our direction. The final piece of our moment that we'd want to know about is the units that go with it, and hopefully that unit piece is already clear from the multiplication. Comes straight out of this. Our sine won't have any unit. Our sine theta, that won't have a unit. It's just a ratio. R, that's a length component. Remember that our forces are separated by distance, so we're going to be able to model some lengths. So the length times the force. So that's going to have units of force. So length times force, which in US customary is going to be pound-feet. So those of you who know torque from the auto industry, pound-foot of torque is a pretty normal thing, or Newton meter be another thing that we could put up there. So again, keep in mind, this is tending to cause rotation. And so if we think about pound-feet of torque, we're going to have something that causes rotation. So here's my foot, my ruler. And then if I took something that weighed a pound, so about a can of soup, got it handy in my mug, and I put it here at the end, that's going to tend to cause, you can kind of see it flex already, but that's going to tend to cause a rotation around my finger here of 1 pound-foot of moment or torque. On the other hand, if I was thinking about Newton meters, I could have my meter stick, and I could put my quarter pounder with cheese, my 1 Newton out there. So this is my really long spatula. Again, about 1 Newton worth, or 1 Newton meter of moment or torque. So those are my units. This is my basic definition. Now, let's take a look at how we might calculate such a thing. So for example, we talked about how I could find that perpendicular distance r to the line of action of the force. And so I could say that the moment generated by force A is going to be equal to RA perpendicular, that's what I've drawn here, times the force at A. That's going to give me my magnitude. So whatever those values are, I could measure them, I could figure out how hard I'm pushing, and that would give me my magnitude. Now then I also said that I would get positive rotation. Now in scalar notation, instead of drawing arrows in the direction of the axes, which we could do, and in fact when we talk about that in 3D, often we'll do double arrows, our scalar notation is going to have a curlicue. And so you can see I've drawn a counterclockwise curl with a plus in the middle to indicate my positive sign convention. And then I can wrap my hand. So if you see my fingers point in the direction of the curl, still right hand rule, thumb out of the board, that's giving me a positive rotation. It's indicating the rotation this force would generate about point O. And in fact, we'd often do this /O to indicate our origin, because if we pick a different point, we'll get a different magnitude for our moment. So there's how we would do that there. Now, we could also do this in Cartesian vector notation. And if you recall, I just said that when we think of the moment, we're thinking about the axis it tends to rotate about. And so if I look at my Cartesian x, y, and z coordinate system, you can see here where my z has that counterclockwise positive curl. It's rotating about the z-axis, and so get a k unit vector. So that's one way we could do this. Let's look at b. Okay, so I want to draw my perpendicular distance. There's my RB perpendicular for this force B from O. Now I'm going to take my right hand. We're going to follow the right hand rule. Okay, so I can do index finger, and then I can do my middle finger in the direction of the force, and then my thumbs into the board. That's negative. Another way I can do it is I can take my whole hand, start at the origin, R, cross F, and then again, thumb into the board. That's negative. Another mental model to do it is I hold on to the string at O. I've got my rocket on a string, and it's rotating in the clockwise direction. So my moment B about point O is going to be RB perpendicular times the force at B, because I've identified the perpendicular distance. So R times FB, that would give me my magnitude. And my right-hand rule tells me that it's negative. So one option is to draw a curlicue in the negative direction. It's going in the clockwise direction. Alternatively, same magnitude. Draw my positive curl, and then I would put a negative sign in front of it. Now, one of the things that I want to point out is, remember, when we do a negative sign on a vector, that means that we're flipping the direction of the arrow. So that's going to be pointing in the opposite direction. So both of those are options, but you wouldn't want to do both the negative sign and the negative curl unless, in fact, you meant the positive, but that would be confusing. Don't do that. Positive also means that my thumb, again, R cross F, my thumb's pointing into the board, so that's going to be the negative Z direction that it's rotating about. So negative RB perpendicular FB in the K direction. All right, pause the video. Check out force C. How would you break that down? Hopefully you gave that a shot. I'm going to walk you through it. We first start off by identifying our perpendicular distance, RC. Our magnitude then, the moment generated by force C about point O, is going to be equal to the perpendicular distance there times force C. How about the direction? Is it positive or negative? Well, if I do my right hand rule, index finger R, cross F for the middle finger, thumb out of the board. That looks positive to me. Or R, cross F, thumb out of the board, positive. Or hold it here, put a rocket on a string, rotating in the counterclockwise direction, positive. Scalar notation, like so. About the z-axis, Cartesian vector notation, like so. So we've looked at these three different moments, like so. And in fact, we could come in here and we could calculate the moments. We could come up with what we'll call an equivalent system. We'll talk about that more in another lecture. But an equivalent system that does the same thing, but rather than identifying the forces independently, we can think of the moments that they're generating. So our equivalent system might look something like this, where we have point O, and then we have the moments acting on each one of these. The moment at A with respect to O is in the counterclockwise direction. The moment B with respect to O is in the clockwise direction. The moment C with respect to O is in the counterclockwise direction. And now what I've indicated is this system uses forces to generate that. And this would be the idea that I'm just going to grab, hold, and twist, and it would be an equivalent system. So we've been able to calculate all these different things, and the axis is running straight out of the board. That's my positive K direction, straight out of the board. All right, so we have that going for us. We've thought about how we can do these different moments. Now, the last thing we might want to do is calculate a resultant moment. So when we were talking about forces, we said that if we had multiple forces, say that we were walking multiple dogs at the same time, and they were all pulling on their leashes, we'd have multiple forces, but we're ultimately going to be experiencing one resultant force. We added up all those forces using our vectors. Now, in the case of moments, we can have the same thing. We can have all these individual twists working in the same direction. It's a little harder to build a good mental model for that, but you can have all these different twists happening on a system, and our resultant moment is going to sum all those moments up. So our resultant moment would simply be the sum of all these applied moments. The key being here, we have to keep in mind what our origin is. Because again, if we move our origin, we can pick any point we want. If we move our origin, all of our perpendicular distances would change and our magnitude of our moment would change. But our resultant moment would be the same between the two systems about some common point. So the idea here is we're going to sum up the moments. And so if we were to do this in Cartesian vector notation for this particular system that we've looked at here, our resultant moment about point O would be RA perpendicular times FA minus RB perpendicular times FB plus RC perpendicular times FC. So I've done some line wrapping, add up all the values, and then because it's Cartesian vector notation, what I'm doing is I'm going to collect that K unit vector and put it out here at the end, like so. And we're keeping track of our positive and negative moment values because some of it's encouraging. So moment at C, moment at A, those are both encouraging clockwise positive rotation. And B, sorry, right-hand rule, is causing that negative rotation, resisting the other two. So this might in fact add up to 0 because yay, nothing moves. In scalar notation, we can do the same thing where we could collect the terms. Now, the tricky place will be when we look at a negative moment. If we've drawn the arrow in the negative direction, we're going to have to reintroduce that negative sign. So most of the time, I'm going to encourage you to draw the positive moment sign convention, our assumption here, and then put the negative sign if it's in the opposite direction, just like we did for our resultant forces. So when we think about our resultant moment in Cartesian vector notation, we could do exactly the same thing, just add up all the pieces. RA perpendicular times FA minus RB perpendicular times FB plus RC perpendicular times FC. And then I just tag onto the end that counterclockwise sign convention, like so. All right, so let's review real quick. Our moments, non-concurrent force systems, are going to have distances, which means we can model things with length, so that's useful. We haven't really talked about that yet. They're going to cause rotation, so a moment's going to tend to cause rotation. We said that we'll use our magnitude will be the cross product, R cross F, or the position vector from the origin to where the force is applied times the across the force vector. Right now, we said that we can do that manually by hand, literally using the right-hand rule, in which case we would take the perpendicular distance times the full force, or the perpendicular component of the force times the full distance. Again, we'll work a problem in class where we look at those two different options. And then that would give us the magnitude with units of pound feet or Newton meters. And then we'd use our right-hand rule where we do R cross F, and then our thumb points about the axis of rotation, or R cross F, and our thumb points about the axis of rotation. Or if we're in 2D, we can think about it doing counterclockwise positive rotation. Our resultant moment lets us add all these things up because they're all pointed in the same direction in 2D. That is either about the K direction in either the positive or negative rotation. So we can add them all up and life is good. So this is moments for 2D non-concurrent force systems. I look forward to working a problem with you in class.